After studying the confidence interval and hypothesis testing for variance of a single population, we will talk about the confidence intervals and hypothesis tests for ratio of two variances. So this is just like we first talk about mu, and then we talk about, so this is for single population. Okay, so this is for single population. For this is for two populations. So we talk about mu1 minus mu2. Then we just start with variances and we talk about sigma square. Now we will talk about sigma 1 squared, not minus, but because we are dealing with the variances, or we have a random variable which deals with the um, this ratio. Hence, we will talk about the ratio of two variances. So just like we use x bar, which is the um, point estimator for mu. We just use s square, which is the point estimator for sigma square. We used x1 bar minus x2 bar, which is the estimator for mu1 minus mu2, point estimator, right? Now we would use a point estimator for sigma 1 square divided by sigma 2 square to exact information for the very ratio of two variances. As you might guess, we will use s1 square divided by s2 square. So how to use this? How to use this? Remember, we just say from central limit theorem or from T distribution, we know the distribution of x1 bar minus mu divided by S over root n or sigma over root n. How about this? We say that I have in minus 1 S squared divided by sigma square, right? And how about this one? We say that, well, this is also normal or this is also T distributed. Hence, I need a distribution for this one. Okay, so well, distribution of what is the distribution of s1 squared over s2 squared? What is the corresponding distribution? Well, it turns out that s1 square over sigma 1 square divided by s2 square over sigma 2 square, which is sigma 2 square s1 square over sigma 1 square s2 square. So this is a f random variable. This is a weird random variable because it has two degrees of freedoms, v1 and v2. So this is f random variable with v1 degrees of freedom, which is n minus 1, so which is in the denominator. So this is n1. So there are n1 items there and n2 items there. So this is n1 minus 1 over n2 minus 1 degrees of freedom. Just like the chi-square, f is not symmetric. All of its values are 0. Hence, I cannot say this is f sub alpha over 2, which leaves an area of alpha over 2 to the right. And this is minus f alpha over 2. Okay, you cannot say this. This is not true because, again, there is no symmetry for the f distribution. Okay, there is no symmetry for this one. Okay. Um, so, um, right. And we will use this random variable to make, remember, to make what first hypothesis test, and we will make confidence or construct confidence intervals using this random variable. So it's a bit forward, but so remember, this is the probability of f random variable between f1 minus alpha over 2, okay, f1 minus alpha over 2, and f alpha over 2, f alpha over 2. So what is the probability that the f is between this one and this one? That's equal to 1 minus alpha. Okay, that's the region here. That's 1 minus alpha. So instead of f, I will just write s1 square over sigma 1 square, s2 square over sigma 2 square, and then make some algebra and leave sigma 1 square, sigma 2 square alone there and find the confidence interval. But before, let's make our hypothesis test. So again, remember step one is the hypothesis, okay? You just write the hypothesis there. So step 2, your test statistic. Well, we know that this is F distributed, sigma 2 square S1 square, sigma 1 square S2 square with N1 minus 1 and 2 minus 1 degrees of freedoms. Okay, this is your test statistic, test stats, which is a random variable in fact. So step 3 is your critical region or what? Rejection region. This is a rejection region. So that's again simple. F1 minus alpha over 2, F alpha over 2. This is at the left and this is at the right. Calculate your F observed. F observed is calculated from here. So we will be given S1 and S2 squares. And well, we will assume that I know them, or um, okay, so this is S1 square and S2 square. Okay, these are just calculated. And sigma 1 and sigma 2 square, how do we calculate them? It just comes from the hypothesis. Okay, so the hypothesis says that sigma 1 is equal to sigma 2. What does it mean? Sigma 1 is equal to sigma 2 means that sigma 1 square, sigma 2 square divided by sigma 1 square, that's equal to 1. Okay, that's equal to 1. Great. Then, if F observed is in the critical region, reject the hypothesis, otherwise don't reject. So assume I have 8 students from Özü and 10 students from Yıldız Technical University, and measure their heights to see that S1 is equal to 4. Okay, so Özü, the sample standard deviation is 4 there, and S2 is equal to 5 there. So using a significance level of alpha 0.10, can you say that their variances are equal to each other? Of course, in order to make this test, again, what is our assumption? Our assumption is that the height of the students in both universities are normally distributed. Okay, so 80 is your null hypothesis is sigma 1 is equal to sigma 2 versus sigma 1 is not equal to sigma 2. So we just go to the table and check F sub 005 with 7 degrees of freedom and 9 degrees of freedom. It turns out that that's equal to 3.29. Okay. Okay. So this is the statistical table for F random variable. So just look at these. This is F sub 005, F sub 005. So this table just gives you the F values, which is an area of 5% or 0.005 to the right. So for example, let's check this one. Oh, I don't know, let's check this one. Okay, 4.15. So what is this? So this is simply, just look at here, this is 8 degrees of freedom, okay? 6, 7, 8 degrees of freedom and 6 degrees of freedom here. This is V2 and this is V1. So how to write 4.15? Let me just write it here. So the probability that, okay. Okay, I don't know whether I can write it here or not. Okay, so this is 4.15. So let me just do it like this and open my whiteboard. Okay. Okay, so what does this mean? This is the probability that, okay, sorry. This is the probability that, sorry for this large thing. So this is the probability that your F random variable, okay, F random variable is smaller than, not smaller than, okay, smaller than 4.15, right? That's equal to 1 minus 0.05, which is equal to 0.95. But this V random variable is how many degrees of freedom? With 8 and what? 6 degrees of freedom, right? So this number is 4.15 is equal to, you can just commented like this. Or let's look at this one, 3.20, 3.20. So that's the probability that, let me just write it like this. F is greater than what? 3.20. Again, that's equal to 0.05, okay? Because you are just writing greater than. And this F is how many degrees of freedom? With 5 degrees of freedom and 11 degrees of freedom, okay? So it is something like this. Just plot it is, oh, this is F random variable, and it is an area of 0.005 there, okay? So this is the 0.05 there, and this is the F random variable. Okay, just go back here. So this is 3.29, okay? So this is the F value which leaves an area of 0.05 to the right. Let me just plot it. Just like this. This is 0.05, 0.05. Well, this is the F random variable with how many degrees of freedom? V1 equal to 7, V2 is equal to 9. Why 7, why 9? Because I have, this is N1 minus 1, this is N2 minus 1, which is 8 minus 1, 7, and this is 10 minus 1, which is equal to 9. So this value is equal to 3.29. Okay? And how about 1 minus alpha over 2 or f sub 0.19 with 7 and 9 degrees of freedom? Well, there is a nice property for this one. Okay, so what does it say? It says that f of 1 minus alpha over 2 with some v1 and v2 degrees of freedom. Well, you can just write it as 1 over f alpha over 2, you see this? I have just changed the value here, okay? 1 minus alpha and alpha divided by now V2, V1 degrees of freedom, okay? That's a very nice property of a random variable. So instead of, so remember, I don't have any symmetry, hence I cannot say f alpha over 2 is not equal to minus f1 minus alpha over 2. But instead of this, I have this this thing, right? So as you can see, f of 0.95 with 7 and 9 degrees of freedom is equal to 1 divided f 1 over f 0.05 with 9 and 7 degrees of freedom, which is 1 divided by 3.16. Okay, so what is 3.16? This is f 0. F sub 0.05 with how many degrees of freedom? With 9 and 7 degrees of freedom, okay, which is equal to 0.27. Okay, so what is observed f? So this is f observed. Sorry, so this is, let me just write it, f observed. S1 S square, S1 square, S2 square, sigma 2 square, sigma 1 square. So sigma 2 square over sigma 1 square, it just comes from the hypothesis. The hypothesis says that, well, they are equal to each other, right? Hence, this is equal to 1 from hypothesis, from H0, from H0. Hence, S1 square divided by S2 square, which is 4 square, 5 square, and that's equal to 0.64. And 0.64 is between the left critical value and right critical value. Hence, it's not in the critical region. That's why we do not reject H0. Okay? So our F observed, this is F observed. F observed is not in the critical region. Okay, critical region. Hence, we do not reject H0. Hence, we cannot say that, well, their variances are not equal to each other. Okay? Now, let's look at the confidence interval for ratio of two variances. So, as I said, so this is the general formula that we use. Probability that f1 minus alpha over 2, f, this is f alpha over 2, that's equal to 1 minus alpha. So instead of f, I just write the definition of our random variables, which is s1 squared divided by sigma 1 squared, s2 squared divided by sigma 2 squared. And after some, so this is what I write, what I did here, okay? Then, but after some algebra, okay, some algebra. So let's say using some algebra, using some algebra, right? I can just write this. So the confidence interval for ratio of two variances is given by this one. Okay. So again, remember, so this is f alpha over 2 and this is f alpha over 2 as well. Why? So I just use this identity. In fact, this is something like this, S1. This is equivalent to this. In fact, this was this times 1 divided by f 1 minus alpha over 2 v1 v2 degrees of freedom. But instead of this one, I just write what? Instead of this one, I just said this is equal to 1 over f alpha over 2 v2 v1. If you just write it there and just take the reciprocal of this, then you have this number, right? Okay, so just look at this one, okay? f1 minus alpha over 2. So this is what we said before. That's great. And these are the critical values of f distribution. Okay. And let's look at the example here. So in Istanbul Boğazı, what we did is we just measured the mean salt content, okay, at two stations. So the first station says that, well, the average weight is 3.84 with standard deviation of 3.07. And in the second one with 12 samples, it's 1.49 with 0.8. So assuming the normal population variance to be unequal. So remember, we just solved this question in the when we are just making confidence intervals or hypothesis tests for what? For two means. We just solved this question. Remember, in that question, we said that, okay, we assume that the variances are equal. So in order to justify this assumption, what we will do is we will just make a 98% confidence intervals for sigma 1 square over sigma 2 square or sigma 1 over sigma 2. Okay. So, okay, these are the data we are given. So alpha is equal to 0.02, which means I need F001, okay, F001, 11, 14, and 14, 11, which is 4.30 and 3.87. So you can just check it. You can just check it from the book. So here you can see that this is again F table with V1 degrees of freedom here and V2 degrees of freedom here, right? So remember what we are searching for, it was, so V1 was 12, V2 was 15, so I need 11 and 14 degrees of freedom. So, okay. So I need, just go back. So I need 14 and 11 and 11 and 14. Okay. So I don't have 11 and 14 in the table. So 11 and 14, it will be somewhere here, hopefully somewhere in between. Okay. And for the other one, so this is 14 and this is it. The other one is very close to, the other one will be very close to this one as well, 4.25. Okay. So let's look at the numbers. Well, that's what? 4.30, 14 and 11, 14 and 11, 4.25, 4.30. Okay, that's very close. And the other one, 11 and 14, that's 3.87. 3.87, it's just in between. Okay, it's just the number in between. That's great. So the confidence interval is, I just plug in the numbers, okay? S squared, this is S squared, and this is S1 squared, so this is S2 squared times 1 divided by 430, which is the value here, okay? And this is the value there, okay? And after some algebra, you see that sigma 1 squared over sigma 2 squared is between 3.425. And in fact, sigma 1 over sigma 2 is between the confidence intervals between 1.851 and 7.549. So what does this mean? Well, it means that, well, I cannot say sigma 1 is equal to sigma 2 because I am 98% sure that the ratio is at least 1.851, okay? Which means, well, I cannot say that both variances or both standard deviations are not equal to each other. Okay, so we were correct in assuming that the variances are not equal to each other. Okay, so this assumption was correct.